Welcome everyone to Minerals and Metals for Sustainability Week 5. Week 5? Yes, Week 5. And we're going to talk in Lecture 5A on the heterogeneous distribution of metal resources. So this is Chapter 2 of the textbook, although I have modified it somewhat from the chapter. So this is just a map of the Earth. With locations of different deposits by commodity. Now we'll come back to a better map than this one, but it's just to get your eye in to see that, large areas of the planet don't have ore deposits. And so the question I have for people is that because there's no ore deposits, say in Greenland or large parts of Russia or let's see, parts of Asia and Northern Africa and central part of South America and central Canada or West Central Canada and the United States? Or is that from lack of exploration? Anybody got an answer to that question? John?
Lack of exploration.
Yeah, you're partly right. And
well, yeah, I mean, you can't explore under the snow of Russia or the Sahara Desert. It's tough or whatever. Part of it's country and politics. But yeah.
It's also geodynamic setting. So you're partly right, and it's partly to do with the geology. So, for example, in the Western Canadian Sedimentary Basin, there's no metal deposits because it's full of oil. So the rock, the geodynamic setting and the rock types are just not conducive to forming metal deposits. Although people are now looking at the brines associated with oil fields as potential lithium resources, for example. Okay, so what we're going to talk about in this particular lecture, we're going to talk about the global distribution of ore deposits. And the chapter really discusses the heterogeneous distribution in space, but we also need to think about the heterogeneous distribution in time. And in a subsequent lecture later on in the course, Bob's going to talk a lot more about that. And the other main point here is there's a strong link between plate tectonics and ore formation. Although, if you want to read some of Bob's papers, you can get the idea, and you would get the idea that when modern style plate tectonics started is not agreed on. Estimates range from, around 1 billion years to 4.2 or 3 or 4 billion years, depending on who you want to believe. Okay, so one of the key things that we want to consider, in which the chapter discusses, is the fact that metals, as well as oil and gas, are non-renewable resources for the most part, at least on the time scale of humanity. We can recycle metals, we can reuse things like diamonds and gold and so forth, but by and large, we need more metals, which we will with the greening economy and moving away from fossil fuels and more to a battery style technology. We need more metals. And so it's important to understand that these are non-renewable. And so the tension becomes, as we use less fossil fuels, we need more mining. And the chapter makes some rather iffy comments about environmentalists saying we can't have either. I'm not sure that's quite true, but nevertheless, the land space that mines currently occupy is a fairly small proportion of the Earth's surface, or land surface. But obviously that would need to grow to meet our new economy. And the other question that the textbook asks is the Earth the only planet in the solar system with ore deposits not formed by bombardment, in other words, by plate tectonics? And so that's a good question. To form an ore deposit, do we need plate tectonics? Or is it just on Earth, plate tectonics and ore deposits are intimately linked? And that's something we could discuss later on, or you could ponder. The chart shows ore grades for Australia, but this is sort of true globally. It just happened to be the nicest figure I could find, going back from 1844 up to the near present. And what you can see is that over time, for most commodities, the ore grade that's being mined, or that is economic, has decreased. So why do you think that is? Anybody have some thoughts?
You go for the easiest and cheapest stuff first.
Yeah, all the near surface stuff is being mined out. And we have to go deeper and deeper, or in a mature mining camp, the high grade stuff is mined first, and then the less and initially less economic stuff is then mined, because it's cheaper to continue mining than it is to build a new mine. Okay, but that begs the question, at what point, how low is too low? And so if we need more metals, but the ore grade is decreasing, um, what does that mean economically and societally?
Oh, I got a comment on that. It's like this comment, we're going to run out of oil. We'll never run out of oil. What we will run out of is cheap oil.
Yes.
And it's the same thing with minerals. So if the price of gold is $10 an ounce, there's going to be a lot less gold mining than if it's $10,000 an ounce, because the economics. So, people are, the question of when are we going to run out of X is kind of a fool's question. And we'll run out of X when people run out of money.
Yeah. Or run out of the ability to make money doing it. Yes,
there you go.
That's right. What's going on here? Okay. So here's a projection. It's for 2010, but the basic idea and the number of papers is the same. This is just for copper production in millions of tons on the y-axis and year on the x-axis for different jurisdictions. And what it's showing is that the projected production of copper will peak at, what is that, around 2025 this year, 2030, something in that time frame. And then production will decrease. As Bob said, that's going to depend on the economics. But what that chart is really implying is that all the easily mineable stuff is basically nearing at the end of its primary or most productive period. And so again, as we become more future becomes more technological, we need more metals. Perhaps the demand for copper is going to increase. Although, having said that, I saw another analysis which said that copper is actually going to increase very little beyond about 2025. So it depends on whose projection. But nevertheless, it begs the question: where are these metals going to come from? And in the mineral exploration business, which I'm involved with, the idea is we need to go deeper, because most of the near surface deposits have already been found. And the trick with going deeper is, how do you see that deep into the Earth's crust to find new resources? And it's a conundrum. So here's a nicer.
Can I comment? I raised my hand, but you didn't notice it, so I'm just going to interrupt. So one of the great stories in the discussion between the doomsayers and those who are, let's say, the utopians and the dystopians, is a bet made in an organization called the Club of Rome between two people. Both of them were at Stanford, I believe. And one of them bet that, this was 1975, one of them bet that we would soon be running out of everything and that prices were going to go through the roof. And the other person said, well, no. And so the bet was based on the price of a commodity, I think 10 years after the bet was made, or 20 years after the bet was made. And it was basically, we know what the price of the commodity is in 1975. The winner will be decided, or maybe it was a basket of commodities, copper, other things. And one person said the price will be higher and the other person said the price will be lower. And it was the person who bet that the price would be lower that won. So that is a very interesting perspective. Now, that doesn't mean that things aren't going to start going. It just sort of points out the difficulty of predicting the future. Despite how much confidence people have about predicting the future, they're rarely right. The other thing I wanted to point was, we rarely talk about the benefits of global warming for obvious reasons, but the prospects of the retreat of the ice cap and permafrost and things like that from northern Asia, Greenland, and Canada for mineral exploration are, let's say, encouraging for those that are looking for more deposits. And that could get me in trouble, but I don't think it will get me from getting fired because I didn't say anything about gender.
Yeah, I mean, we'll have more real estate because we've removed some of the overburden. And when we go to this map here, so if we look at Greenland, which is a great example of what you just said, Bob, there are deposits around the margins of Greenland. They're a little hard to see on there, but they're there. There's a massive rare earth potential deposit on Greenland, which may be part of the reason why some people want to take over Greenland. But most of it's covered in ice, and so who knows what kind of mineral resources exist underneath the ice. Anyway, so this is another map showing the distribution of ore deposits in space. It's a little more clear than the one at the beginning of the lecture. And again, you can see large parts of the interior seaway are deposit poor. And again, it's because of the rock types and the tectonics. They're metal deposit poor, but oil rich, just as an example. The other thing I like about this map is that it also has on the seafloor some of the known deposits on the seafloor, although we will talk about seafloor mining in a future lecture. Okay, so ore deposits are concentrated in certain parts of the world. I'll come back to that. Okay, so the rest there, distribution is linked to plate tectonics for most ore deposit types. And so this is from the textbook, and it shows that in the Archean, in their formulation, that we had lots of subduction, lots of mantle plume. So here we have a mantle plume coming up from the core mantle boundary, giving us a hot spot. We have arcs with subduction. We have more subduction here, slab melting. If this model is correct, slabs presumably were able to melt because of the hotter mantle than today. Although, again, some people argue that slabs do melt in the modern environments when they're young and hot. And then they contrast that with a more modern style tectonics. And in this case, in this diagram, they have whole mantle convection in the modern and two mantle convection or two layer convection in the Archean. Again, people dispute how the mantle actually convects and whether it's whole mantle or not, but there you go. And again, as I've already mentioned, people also argue about whether there was subduction in the Archean or not.
Question from Bob the Silent.
Of course.
You see how hard I'm trying to be well behaved. Thank you, Clint. So I have to comment that my interest, Matt works at a university that's very focused on mining. I do not, and my interest in mining and mineral came from the rather unsupportive response of the geologic communities to some of my ideas about when plate tectonics began, which were based on academic lines like ophiolites and blue schists and things that have no economic value. But there's this whole other world of interesting information from a completely different community in the mining industry, in economic geology, and that attracted me because they had not already taken a position on when plate tectonics started, because they don't really care about it. They just want to find it, right? So anything that they're potentially more sympathetic to some radical geological ideas, but I just had to comment on that.
Yeah. And you have published on economic geology aspects of when plate tectonics started. I think you had a paper on kimberlites, diamonds, and things like that.
Yes, we did, and it's very highly cited. You just remember yourself as a co-author.
I do actually remember that.
And
Okay.
your hand is still up.
I mean, maybe he has more to say.
Maybe he does, but your hand is still up.
Well, the problem is I have trouble figuring out how to lower my hand. I will continue to work on that while Matt continues to
I
lecture.
will continue. I will continue.
Self-reflection.
Self-reflection. So here's a cross section of, let's call it the ocean, the Pacific Ocean basin, just for argument's sake. And so if that was true, we would have on the western side, we would have oceanic subduction, say in the Mariana Arc, as an example. And so we have the subducting plate, and we could see that the kinds of deposits that would be associated with that tectonic regime would be porphyry copper deposits, epithermal gold deposits, and in the forearc or the back arc, the arrows here in the forearc, we'd have VMS, or volcanogenic massive sulfide deposits. These are seafloor deposits that we'll talk a lot more about as we go along in the course. And so this is associated with island arc environments. And in the Western Pacific, there are large islands with lots of porphyry copper deposits and lots of gold deposits. Then if we go back to the east, we'll ignore Hawaii for now. We have the East Pacific Rise, for example. So there are active hydrothermal systems on the sea floor along the East Pacific Rise, some of which are forming potential ore deposits. Again, we'll come back to mining the seafloor in a future time. And then as we go to the east further, we see we've subducting now underneath a continent. And so associated with that, with orogenesis, with mountain building, we have, again, porphyry deposits, epithermal deposits, with lots of gold vein deposits. And then if we go in the back arc, so we're rifting continental crust in the back arc, we have our sediment-hosted type deposits, evaporate deposits, and then on the platform, should be underwater, but it's not in this diagram, we have MVT deposits, or Mississippi Valley type deposits, which are lead and zinc rich carbonate hosted deposits. So you can see that large classes of ore deposit are at least in the modern as we perceive it, we're fundamentally linked to plate tectonics. So we can think about the distribution in space, but also the distribution in time. So it's kind of a complicated diagram, and I include it mostly for your edification, but I just want to highlight, for example, VMS deposits. If we go back in time, so the scale goes back to 3 billion years to the Archean, and we can see that around 2.7 billion years ago, there's a large number of VMS deposits, and then there's a big gap. And then there's a large number of VMS deposits around 1.9 billion years ago. And then there's another big gap, the so-called boring billion, until we get to the more modern, to the Paleozoic, again, as we get a lot more VMS deposits associated with the last 500-600 million years or so. Yes, Bob.
So I look at this diagram, and your eye doesn't know where to go. It goes to the reds and the dots. So one of the reds with no dots is the Grenville, which is very near to you. Is Queen's University built on the Grenville, or?
It's just to the north of us.
Just, okay. So it's like, okay, it's basically saying that was an event that was very much like what's going on today and what happened in the Phanerozoic. But it's like, okay, then where are the similar ore deposits? So I really like this diagram.
And you mentioned something very interesting, because there are ore deposits in the Grenville, but they are difficult to define because they're so metamorphosed, right? The Grenville has been heavily metamorphosed and eroded, more so than, say, some of the greenstone belts in the Canadian Shield. And so it may be that the ore deposits have been metamorphosed to something unrecognizable, or they've been removed. So there may be other reasons for that, a preservation issue. The other interesting one is the porphyry copper deposits in the middle here, and you can see that most porphyry copper deposits formed in the last couple of 100 million years. There's a few scatterings in the early, in around 2.7 again, but by and large, porphyry copper deposits are a fairly modern phenomena, and the reasons for that, one can argue it's probably primarily a preservation issue because they represent high islands or high mountains and can get easily eroded. But maybe there's a plate tectonic explanation embedded within that data. And this is just the same diagram.
So Madison's got a question.
Oh, go for it, Madison.
Yeah, so I found this really interesting. In the book, they mentioned that if humans had sort of evolved 1 million or 5 million years earlier, we wouldn't have found any metals in the Pacific.
Can you hold that question?
Sure.
We're coming to that. That's a great.
Okay.
Yes, I have highlighted that sentence in my copy. Okay, so again, just more deposit types. Interesting, uranium deposits are not associated with the reds, right? So these are because the big uranium deposits form in big sedimentary basins. Some of the biggest deposits are in Canada, just as a where it says Athabasca there, those are some of the huge uranium deposits in Canada. And this is just a diagram for gold deposits or for gold resources, showing some of the major continental constructions: Kenoraland, Columbia, Rodinia, Gondwana, Pangaea. And you can see the bottom chart shows the relative amounts of crustal growth. And then they seem to link with gold mineralization, although again, around that Grenville time, where's the gold? So it's interesting. And this diagram, and I don't have the source because it's just on my hard drive, but they have an onset of modern style plate tectonics at about 1 billion. Put that in for you, Bob. Okay, so we need to form an ore deposit. Well, we talked about mineral systems last time, but so this is the way that the textbook frames it. So we need a geodynamic setting. So we need the broad tectonic framework. Just as an example, porphyry copper deposits form along convergent margins or in post-convergent margins as well. We need a fertility aspect of it because we need to have an anomalous concentration of metals to start with, or at least a mechanism by which we can concentrate metals. And then we need a suitable architecture. That is, we need to have the transport pathways, faults, pores, that sort of thing, and a receiving environment to then form the deposit, which can be a structural control or a redox control, as we talked about previously. And finally, we got to preserve it. And so, certain kinds of deposits are easier to preserve than other kinds of deposits. So back arc VMS deposits are relatively easy to preserve, whereas porphyry copper deposits are relatively difficult to preserve. Bob.
Yeah, so this is reminiscent of your previous presentation about mineralizing systems. So what is the difference between this and a mineralizing system? The main thing I can see is the geodynamic setting and the preservation.
Yeah, this adds the preservation, although some of the other ones allude to it. This is just the way the textbook has framed it. And as I mentioned or showed last time, there are lots of different ways that people have framed the mineralizing system approach, ranging from very generic, which I would call this a very generic perspective. And this figures from the textbook, for example, so it's not specific to any deposit type, going down to single deposit type or class of mineral systems approaches, which we showed last time with magmatic ore deposits and VMS deposits and porphyry deposits.
It might be worth, with thinking about student projects, building on the mineralizing system is not a bad idea. Because my sense of the mineralization system philosophy is that it's not as well developed yet as, say, the petroleum system philosophy.
Oh, not at all. Yeah, no, I agree. And in fact, if I remember correctly, I think mineral system occurs once in that chapter as a reference. So again, we have fertility, architecture, and tectonic setting interacting, I guess, or a Venn diagram with some kind of sweet spot in the middle in the red, and then we have to add the preservation. And so the endowment of ore that we have is all of these things. And yeah, what's missing from this formulation is we have to concentrate things. It's not just about the source. We have to concentrate things in a trap environment. I guess that's what's missing. Okay, so in the textbook, they show this diagram of the so-called ring of fire, which you have to imagine as a ring because they've placed the Atlantic Ocean in the middle. Most maps will put the Pacific Ocean in the middle, in which case you would see the ring of fire all the way around the Pacific Ocean. So it's over on the extreme right here for the Western Pacific. And then they make this claim. If humans had evolved even 1 to 5 million years earlier, there would have been far fewer metal resources around the Pacific margin to exploit. So I took that to mean that what they meant was the Ring of Fire has all these deposits today, and therefore it's a good thing that we evolved when we did because those deposits are here. Bob has a different interpretation of, or a potential different interpretation of what they said, but I'm interested to know what students think about that statement.
And Madison has an opinion.
And she does, exactly. That's right. Sorry, Madison.
You're muted.
Less of an opinion. I was more just I found that to be a really interesting statement. And I was wondering if the idea was that those minerals all existed, but prior to that, they just were unavailable because they were so deep, or potentially they hadn't been concentrated. So they were available at the surface, but in such low quantities or such a low percentage by weight that you wouldn't actually be able to mine it. But I wasn't sure which one, or some combination of both.
That's interesting. Anybody else have any thoughts? You're muted, Bob.
I thought it was because if people were around 1 to 5 million years earlier, we would have exhausted all of the ore deposits. But that's
I don't think that's what they meant, but that's an interesting interpretation.
I don't think the statement is verifiable. I think it's, I think it should have been, somebody should have said, what, if you're going to say this, you better explain it.
Yeah, and it's not. I mean, in my thinking, the Pacific Ring of Fire has, well, if we look at the Western Pacific, the Pacific Ocean has been, Pacific oceanic crust is up to 180 or so million years old. So it's been subducting for a long time. So I would think that 5 million years ago, there was just as many ore deposits. Some of them may have been eroded in the last 5 million years, but then new ones have been created in the last 5 million years. And so I think it's a little silly to say that we would have been far fewer ore deposits or metal resources. That's just my feeling. But I think it's something important to think about, though.
It would be one of those, the present is the key to the past things. And I would say 5 million years wouldn't have seen that much of a difference. So you'd have, of course you would have had the same stuff.
Yeah,
in different places.
I agree, Glenn. Yeah. Okay. Nobody has any other thoughts? I thought that might generate some good discussion, but I guess people are shy. It's okay. All right, we'll move on. So the textbook includes a table 2.1, and we're not going to go through this in exhaustive detail, but really it's listing the major classes of mineral that the textbook talks about. So abundant minerals, scarce critical minerals, rare critical minerals, and precious metals, and is showing them by global distribution of the top 5 countries from which these metals are extracted. And the main thing to take away from this is that there's a small number of countries that appear multiple times. So if you look at it, China's there a lot, Australia's there a lot, United States and Canada, Brazil. But there's some other ones that sprinkled in throughout there. But those are sort of the major countries that are producing the bulk of the metals that we use. Yes, medicine.
I was curious for this chart, how dependent this is basically on those countries actually having explored or having been explored by someone, as well as the countries kind of being upfront about their mineral resources. And so like how, yeah, just how legit this is versus it's just sort of more of a list of countries that have like open publishing and have resources to explore.
Yeah, that's an excellent question. And I think there's probably a variety of ways to answer it. I think one of it, you may be right that there's variable degrees of exploration. So, less well-developed countries perhaps have had less exploration, although mining companies, mineral exploration companies from more developed countries have certainly operated in other places around the world extensively. There's also issues related to perhaps environmental stewardship. So, environmental legislation in China may be, and I don't know for sure, but it may be less stringent than it is in, say, North America. So that
Oh yeah, you do. It's less stringent.
I'm being politically correct here. So I may want to visit China one day.
But it says it's based on reserves, right? So reserves, and these are reserves on company websites. So it's not really telling you what's in the ground. It's basically telling you where people have found it and have made the calculation.
Yeah, so there's an economic underpinning to that. Because
what's the difference between compliant and non-compliant reserves?
Where's that?
It's
down
it's
there.
in the footnotes of the explanation.
Yeah, between compliant and various companies.
I never heard of the difference.
Well, compliant would be, so in Canada, we have what's called a 43-101, which is reporting that companies do, which is it has to meet certain standards to be legitimately reported for purposes of stock exchange. In Australia, they have one, I think it's called JORC, which is a similar sort of governing body, and not all countries would have such compliance with respect to reporting of or deposit of reserves. Right. In Canada, you have to have real data backing up your reporting of a certain reserve.
So you wonder what non-compliant means. It means it doesn't have that level of oversight.
That's right.
I would point out that if you get this off of company websites, companies want their stockholders to know certain things. And particularly in oil, they will say things, and sometimes they turn out to be true. Sometimes they don't.
What that would, of course, never happen in the mining industry, Clinton.
Oh, never.
So if the distinction between reserve and resource comes down to like if it's economical to actually mine it, you could have two countries where they had the exact same resources, but only one of them would actually count as a reserve if, say, like they had less environmental restrictions and cheaper labor. So it's
yes. Yes.
So basically, like geologists shouldn't really use these numbers because they're not a true representation of what's there. It's more of like being filtered through the economics.
Yeah, I mean, I think this chart is really just highlighting the map that I showed earlier of the distribution of deposits around the world. But we'll come to another map in a minute, which speaks to that. This is table 2.2 in the book, and this is the global distribution of production of the trace and precious metals. Again, showing the same thing, but this is now actual production rather than reserves. And so again, you can see China features prominently, Canada, the United States. Okay. So here we have again a map in a different formulation of the heterogeneous distribution of metal resources around the world. And the ones in pink are the ones that have the most metals, or that at least apparently have the most metals, you know, given the caveats of exploration and so forth. You know, what the textbook calls the pink areas highly endowed regions. You know, what the cutoff is, I don't know. I don't remember them actually saying. But nevertheless, you can see that Russia, China, Australia, South America, Canada, I would have put the United States as pink, but that's just me. Yeah, so again, concentrated in certain parts of the world. And then the textbook talks about critical metals and geopolitical risk. And so we can divide the world into different blocks geopolitically. So in orange here, we have NATO countries or NATO aligned countries. And so there are certain advantages to being aligned in NATO in terms of supply chains and so forth. Counteracting that or looked at differently, we have the so-called BRICS nations, or those that are thinking of joining BRICS here. And so again, here we have, you know, the splitting of the globe into these major geopolitical blocks, and that has important ramifications for exploitation and transport of metals around the planet. And that in itself leads to this idea of conflict minerals. And so I don't, the textbook doesn't really talk too much about conflict minerals, but I just sort of introducing it here because it's an important concept, because when we think of supply chains, we also have to consider that, you know, let's say in Canada, we don't want to necessarily buy cobalt from the Democratic Republic of the Congo, which controls about 70% of the global supply of cobalt, because of their human rights and environmental record. And so, and I have very mixed feelings about that, because on the one hand, by not buying cobalt from DRC, you're saying, well, we don't agree with your environmental standards. But on the other hand, you're also not helping the local people. So anyway, there's lots of issues around conflict minerals. You know, you've probably heard of blood diamonds, which are this, again, conflict diamonds coming from parts of the world where there's lots of war and exploitation of people and so forth. So some years ago, when diamonds were first really found in Canada back in the 1990s, in the Northwest Territories, which is where most of the up in here, where most of the diamonds are in Canada. There's other diamond fields, but the main ones are up in the Northwest Territories. And what they actually do is they laser etch a polar bear onto each diamond that has been mined, processed, and cut in the Northwest Territories. So it's like and the Canadians up there were the first people to do that. It's done quite commonly now to laser etch diamonds from where they've come from, where they've been cut. So that's kind of the end of my presentation. Any questions? Comments, complaints?
It's a really good overview, because it's less about geology than pretty much any chapter that we have in the book, or any any lecture that we've given. Would you agree that this is sort of
Mhm.
the least geologic of the lectures?
Yeah. Yeah.
And it sort of points out where we need help from political scientists and, business people. It's
Yeah.
it's like, because the bricks, that was the first time I heard about bricks that I paid attention to it was, in discussing this stuff.
Yeah.
But John had his hands up.
I'm just curious, Matthew, what your opinion is versus the books
On
the rarity of these things, what the future looks like, and
I mean, I tend to fall into the optimist camp, in that sense that, well, I'm the ultimate optimist because if we wipe ourselves out, the planet will carry on. It's done it many times before, wiped out most of the biomass. So I'm an optimist in that perspective, but I'm also an optimist in the sense that, as Bob alluded to earlier, if it's economic, we'll still keep finding metals. And I think human ingenuity is such that if we truly do sort of on the current trajectory, quote unquote, run out of metals, we'll find other ways to extract metals from things we already have, like, for example, mine tailings. So Tom, who's in the class, is working on recovering rare earth elements from mine waters, things like that. So I'm optimistic.
how do you feel about opening up more of North America to mining?
So my perspective on that and is that a company's job is to make money for their shareholders, right? That's its job. And it's government's job to make sure that a mining company, in this case, does it responsibly in a societally relevant and compliant way. And the problem is, I think, that increasingly corporations control government, and so there's less oversight. I think that might be a politically correct way to say it. But I have no problem inherently with mining because, as miners in Canada like to say, if it can't be grown, it's got to be mined. And you know, we can't, if we want, we can't really, given the population we have on the planet, we can't go back to the quote unquote good old days of, as the book alludes to flint tools and so forth, right? It's just unsustainable. So
I should point out that flint was also mined economically.
exactly. And the book does make that point too. Yeah.